Welcome back to another lesson in AP Stat. Today we are going to be moving on to Chapter 3, where we will be looking at scatter plots and correlation and the relationship between two quantitative variables. So when we're looking at the relationship between two quantitative variables, we are looking at two variables. One's called the response variable, one's called the explanatory variable. So a response variable measures the outcome of the study, and the explanatory variable may help or explain or influence any changes in the response variable. You can think of this as the explanatory, meaning that it's the x-axis, and the response variable is the y-axis. So the explanatory variable is like the input into a function, and then the response variable is just the output, the y. But in this case, we're talking about actual context. So we have two quantitative variables, one trying to explain the other. In many studies, the goal is to show that changes in one or more explanatory variables actually cause the changes in the response variable. However, other explanatory response relationships don't involve direct causation. So right now, we're just looking at the relationship between two variables, one the explanatory, one the response. We're not necessarily saying that one causes the other. We just want to know if there is a relationship between them. And I told you that there's always a possibility of having lurking variables or confounding variables. And if you remember the example that I gave from earlier this year about the ice cream sales and the number of shark attacks. Remember, we eventually concluded that ice cream sales don't cause shark attacks, right? But they both increase at the same time, and a lurking variable behind that is the fact that you sell ice cream in the summer and sharks attack humans in the summer. So we're looking at the relationship between two variables, but not necessarily a cause and effect relationship. So in order to look at explanatory and response variables, we're going to look at a scatter plot. And this shows the relationship between two quantitative variables measured on the same individuals. When we're making a scatter plot, we have to decide what goes on each axis. Remember, the explanatory x goes on the x-axis, and then the response will go on the y-axis. Just like you did for your histograms, you want to label your axes and give your scatter plot a title. I should be able to look at your scatter plot and not have to ask you any questions about the context. And then, of course, you want to plot your individual data points. You're going to be making a lot of scatter plots using your calculator. So you're going to be able to copy what you see on your calculator onto the piece of paper that you are handing in to me or to an AP grader. So make sure you are labeling both your X and Y axes and giving your scatter plot a title. So, you know how we described distributions earlier this year? We used CUS, where we talked about sensor, unusual features, shape, and spread. Now we have to find a new acronym to examine scatter plots. So in a scatter plot, we are looking at the overall pattern. And the acronym we're going to use is called FODS, F-O-D-S. So when we're describing a scatter plot, we're looking at the form, the outliers, the direction, and the strength. Okay, so form, outliers, direction, and strength. You should hit all four of those characteristics in order to fully describe your scatter plot. So let's go through each one of those characteristics. So direction. Direction can be positive or it could be negative. We talk about with association. So if it has a positive association, that means as the explanatory variable increases, the response variable increases in general. Or if it has a negative association, it means as the explanatory variable increases, the response variable decreases in general. So this is an example of a negative association. As you can see, it is as the percent taking the SAT increases, the mean math score seems to decrease. So when we're describing this scatter plot, we're looking at form, outliers, direction, and strength. So form. When we're talking about form, I want to know, does it look linear? Does it not look linear? Are there any clusters anywhere? Okay, so we're looking for clusters and linearity. In this chapter, we're going to focus a lot on linear scatter plots. But moving forward, we will look at things that are not linear. And so it's important to decide whether a relationship is a linear relationship or not. So when describing this scatter plot, we can talk about its form. And to me, it looks a little curved, if you were to ask me. I actually think there's two clusters, right? There's a cluster between 0 and 20, is this cluster here, and then there seems to be another cluster over here. So if you're asking me, there are two distinct clusters. And if you look at the answer here, it says there are two distinct clusters of states and two possible outliers. Okay, so we have outliers. This is a possible outlier right here, and this seems to be a possible outlier. Right now, we don't have a mathematical way to describe or to determine an outlier on a scatter plot. We used to have a mathematical way when it was a single variable, right? We had the 1.5 times the IQR. But when we're looking at two quantitative variables, we don't have a mathematical way to. So now we're just looking to observe outliers. So talk about form, direction, outliers, and strength. So it is a moderately strong negative curved relationship. So here we go. Moderately strong. There's a strength. Negative. There's a direction. Curved. There's the form. Okay, so form, direction, strength. And then, of course, we have our two distinct clusters and maybe an outlier or two. And you can point to the outliers if this was a real problem. So you can see we have strength, we have direction, we have form, and then and then our possible outlier is down at the bottom. Okay, so we're describing scatter plots using FODs. All right, so here is a scatter plot where it is points per game as the explanatory and the number of wins as the response variable. Now it should make sense that the more points you score, the more games you win. Okay, so describe it. Direction. In general, it appears that the more points you score, the more games you win, so therefore is a positive association, therefore a positive direction. Form. This seems to be more linear than the last one. So this is definitely a linear pattern. Overall, not perfectly linear, but it's pretty linear. Okay. Strength. It seems to be pretty strong because the points don't vary much from that overall linear pattern. And we'll get more into what makes it strong and what makes it weak. And just looking at this scatter plot, I don't see any outliers to my eye. You could call this point right here, if you really want to, an outlier, but it doesn't seem to deviate too far from the pattern. So therefore, I would say that there are no outliers. So form, outliers, direction, strength, describing a scatter plot. So when we're measuring the strength and direction of a scatter plot, we can actually put a numerical value to it. It's called correlation, okay? Because just by looking at a scatter plot and saying, oh, it's kind of strong or it's moderately weak, sometimes our eyes are not good at judging how strong a linear relationship is. So we need to use our mathematical power to come up with a value that will give us the exact strength of the linear relationship. In order to do that, we have to calculate correlation. Correlation is called R, right? The variable is R. And correlation measures the direction and the strength of a linear relationship between two quantitative variables, but only linear relationships. If you think the form is a curved relationship, you should not use correlation, because correlation is only for linear relationships. Okay, R, which is correlation, is always between -1 and 1. If R is positive, that means it's a positive association, and that's how correlation gives us strength and direction. If R is negative, it means it's a negative association. Any value near 0 is very weak. So the closer you are to -1 or +1, the stronger the relationship is. Okay? You will very rarely, if any, ever see a perfect -1 or +1 relationship, because that means it's a perfect linear relationship. That doesn't really happen in real life. Okay? So correlation, it helps you quantify strength and direction. And we're going to be able to use our calculators to find correlation. So here are some examples of different correlations. You can see at the top left that there seems to be no association here, so therefore correlation is just 0, because there's no way to really make this into a linear relationship. The next one is a correlation of -0.3. It's a little bit more linear. You can see you could draw a line through here. It's still very, very weak. It's negative, but it's a little stronger than having no correlation. The top right is a correlation of 0.5. Then we go to a -0.7, which is getting much stronger. I would call this moderately strong. 0.9, I would call this strong. It is a strong relationship, and it's a positive relationship. And then the last one, -0.99, you can see just how strong that relationship is compared to something like -0.3. It's a very strong negative association. All right, so how do we calculate correlation? Well, there's a very, very complicated formula that you will almost never have to use. However, it's cool to understand. Okay, so let's look at it. Don't be scared. Here it comes. Whoop. All right, let's break this down. If you look at every individual term, you see x1 minus x bar over s of x multiplied by y1 minus y bar over s of x. That formula should look very familiar. What you're doing is you're finding the z-score of every x value and the z-score of every y value. You're standardizing those scores. You're multiplying them together, and then you're adding them to every single data point. When you do that, and then multiply it by what's called 1 divided by the degrees of freedom, which is n minus 1, you get correlation. Okay, so while you're never going to use this formula, we do understand it. It's the z-scores of the x's multiplied by the z-scores of the y's, and then we add them all together. Okay, now the formula itself is complicated. We're not going to use it, but we do have to interpret it and understand how it works. So here are some facts about correlation. 1, correlation makes no distinction between explanatory and response variables. For example, we looked at points per game versus wins, where points per game was the explanatory variable and number of wins was the response variable. If for some reason you got a little confused and you flipped the points per game to the response variable and the wins to the explanatory variable, and you were to calculate R, correlation, you would get the exact same value because it makes no distinction between explanatory and response variables. R does not change when we change the units. So if we were talking about inches versus, and we changed it to centimeters or we changed it to miles, it does not change with units because we're looking at the relationship between the variables, and the relationship doesn't change if we change the units. So if we change units for x, y, or both, the relationship is still the same. Correlation itself, so R has no unit. So if you get an R value of 0.9, it's just 0.9. It's not 0.9 dogs. It's not 0.9 people. It is just 0.9. There's no unit of measurement for R. So when we talk about correlation, be careful. Correlation requires that both variables be quantitative. You can't use correlation when talking about categorical data. Correlation does not describe curved relationships, no matter how strong it is. If something is perfectly quadratic, you cannot use R because R is just for linear relationships. Correlation is not resistant. What does that mean? Well, it means that it's strongly affected by a few outliers. So if you have an outlier or two in your data, you have to point it out because your correlation value will be strongly influenced by those outliers. And we will talk about influential points and outliers as we move along chapter 3. And correlation, while very helpful, is not a complete summary of the two variable data. There's a lot that goes into analyzing the relationship between two variables, and correlation is just one piece of the puzzle. So here is a problem that requires you to make a scatter plot on your calculator. So we're talking about the metabolic rate, which is the rate at which the body consumes energy, is important in studies of weight gain, dieting, and exercise. We have data on the lean body mass and resting metabolic rate for 12 women who are subjects in a study of dieting. Lean body mass, given in kilograms, is a person's weight leaving out all the fat. Metabolic rate is measured in calories burned per 24 hours. The researchers believe that lean body mass is an important influence on the metabolic rate. And they give you the data. So here is the mass and the metabolic rate. Okay? So you should take a second and pause this video to input these two quantitative lists into your calculator using list 1 and list 2. Now that you have input these data points into list 1 and list 2, we are going to use our calculators to create a scatter plot. So let's pull up my TI-84 emulator. If you go to my stat and go to my edit, you will see I have these in list 1 and list 2. List 1 is the lean body mass, and list 2 is the metabolic rate. Now the problem itself said that researchers believe that lean body mass influences metabolic rate. That means lean body mass is the explanatory variable, and the response variable is the metabolic rate. So list 1 is my explanatory variable, and list 2 is my response variable. To make a scatter plot, we're going to go into our stat plots, which is where all of our distributions lie. So if we go into stat plot and go into my first stat plot, I'm going to turn it on, and the very first type of stat plot is a scatter plot. When you hit scatter plot, it's going to ask you for your X and Y list. So your explanatory list and your response list. My explanatory list is in list 1. My response list is in list 2. You can pick whatever mark you want. I choose squares, and then I'll make it blue. Okay. And when we're doing stat plots, remember we want to make sure when we graph it, we put it into a stat window. So we hit zoom 9, which is zoom stat, and we get this lovely picture of a scatter plot. Now looking at this scatter plot, we can describe it. FODS, form, outliers, direction, strength. The form, I would say it's pretty linear. Okay. Outliers, it doesn't seem to be many, or if any outliers. Maybe there's one point right here, which if I hit trace, I could find that point right there. The point 42, 14, 18 could be an outlier if I was being a little nitpicky, maybe. Okay. Direction, definitely a positive association. And strength, well, when doing strength, I want to be able to find correlation. So let's go ahead and find the correlation of this scatter plot. So I'm going to quit. I want a blank screen. I'm going to go into stat, go over to calc, go down to linear regression A plus BX, which is number 8. We're not going to use number 4 because the variables are all mixed up on our formula sheet, which we'll talk about in the next section. So we are really going to use number 8 always. Okay, so it's A plus BX, where B is the slope and A is the y-intercept. And we'll talk about linear regressions a little later, but you need to find the linear regression line in order to find correlation. When you go down to this, you're going to hit enter, and it's going to ask you for your explanatory variable, your response variable, and then you can go ahead and calculate. And this will give you your R value, correlation, which here is 0.876. It will give you R squared, which is called the coefficient of determination, We'll talk about that later. And it'll give you A and B, which are values that are very important that we'll get later. Now, many of you might look at your screen and say, oh no, I don't have R squared in R. That's because your stat diagnostic is off. If you go into mode and you go scroll on down to where it says stat diagnostics, make sure that is flipped on. So right now mine's on, so make sure to go on and hit enter. And once your stat diagnostic is on, if you were to go into calc, linear regression A plus BX, and then you calculate this, it will give you your R squared and R value. Every time you reset your calculator, it turns your stat diagnostic off. I don't know why it does, but it does. Okay, so you have to make sure your stat diagnostic is turned on for you to get R and R squared. So here my R value, 0.876, very strong, clearly positive, so that will give me a positive, strong association. Okay, and that is the end of 3.1, which is about describing scatter plots. We're going to do a lot more calculator work in the next section. I'll see you all soon.